Yeah, so let's take it a step further here. If we do have a conservative vector field. So one more here to check to see if it's conservative. And then if so, find a potential function. So this is the next step that we can take if we know f is conservative. But it has to be conservative for us to take this next step. Okay, so this is P, this is my Q. So to determine if it's conservative, look at the partial P with respect to Y, and then the partial Q with respect to X. I think these are pretty easy. So the partial P with respect to Y. Well, doing it with respect to Y, so it'd be 2x cubed times 4y cubed. And then that's plus x, that doesn't have a y in it, that's 0. So it's just that, 8x cubed, y cubed. 8x cubed, y cubed. Pretty simple partial. What about partial q with respect to x? So that's my q, do that with respect to x. Again, the y is fixed, so that's 8x cubed, y cubed. I'm only doing the derivative with respect to x there. And then y, no x, derivative is 0. Look at that. Got the same thing there, it's conservative. Okay. Well, so if it's conservative, all right, so back to again definition. So if it's conservative, what does that mean? Well, if f is conservative, then there is an f such that gradient of f equals that particular vector function. So there's a gradient function for it. A function whose gradient is equal to. All right. So that's what we're going to play off of here. How are we going to find that potential function? That f is called the potential function. And there, possibly could be more than one, but we're just interested in finding one of them. There's more than one. One's usually plenty of fun. All right. So here's what we're going to do. We're going to call the partial of f with respect to x. That's going to be our p. Right? Because what is the gradient of f? How is it constructed? Or how is it found? If we know f, how do we get the gradient? Let me put it that way. Well, you do the partials. First component is partial with respect to x, and then the second component is the partial with respect to y. That's, if you've got f, that's how you do its gradient. Just do the partials. Now, since we know this is our function, and that's kind of where we're going, or what we want our gradient to equal, doesn't it stand to reason here? So if I want to find f, here's what I know. The gradient of f, the first component is the partial with respect to x. So wouldn't this, since I want the gradient of f equal to f, wouldn't this equal that? That's what I need this first component to be. I need it to be that. The second component, partial with respect to y, it needs to be equal to that. So here's what we're going to do. We're going to set the partial of f with respect to x, and usually, you can write it that way, but so to find this potential function, let p equal the partial of f with respect to x, and q the partial of f with respect to y. So that's how we start this off. Now notice, okay, this is a little different than determining if it's conservative, because there we were doing the partials of p. What we're saying here is our partial of f with respect to x is going to equal p, and the partial of f with respect to y equals q. All right. Okay, so in this case, we've got the partial of f with respect to x, that equals p, which equals, in this case, 2x cubed y to the fourth plus x. And then we also have q equals partial of f with respect to y. So that's, I'm sorry. So the partial of f with respect to y equals q, which equals 2x to the fourth y cubed plus 1. All right. So our goal here, find a potential function. We're finding an f, a little f. This is what we got. We got the partial of f with respect to x, and we got the partial of f with respect to y. How are we going to get back to f? Well, basically, what we're going to do here is, and you can use either one for this. If we use this one, in this case I don't think it'll matter. Sometimes it's easier, one is easier than the other to do this too, but I've got the derivative. How do I get it back to the function? Antiderivative? Integral? So f here then is going to be the integral, in this case, of p with respect to x. Or in other words, the integral of this 2x cubed y to the fourth plus x dx. Which, if they're nice to us, it's a pretty easy one. So this, here's a little, well, easy enough. This is just two things. The y we're holding fixed here. So this would just be antiderivative of that with respect to x, power rule. The new power would be x to the fourth. Y is fixed. We divide that 2 by 4, so it's just 1/2. Get me there? Just antiderivative. And then plus x, so that'd be plus 1/2 x squared. Now, indefinites. We usually add plus c. There's a little bit, call it a wrinkle, a little bit of a hitch with the constant here. It's kind of more than a constant. Remember when we started this thing, we know it's a two-variable function, an x and a y. And so this is saying partial with respect to x. Well, when you do the partial with respect to x, the y is a fixed, right? Y is considered like a constant when we're doing this. So the kicker is the plus c here could be potentially a function of y. You with me? They call it h of y, I guess, because we got f's. I don't know why it could just go with g, but they call it h of y. The constant could be, let's say, C could be a function of y, or is. Not necessarily a function is what I mean. So we have to not say C, we have to say h of y, some function of y. And that's because we're doing the partial here with respect to x. Now, if I had done this one, the integration over here, what would the C be over here? A function of, this one's based on a partial with respect to y. So if I did this integration, what would the constant be here? A function of x. A function of x, right? H of x, yeah. H of x. So kind of see the idea there. Because this one's partial with respect to x, the constant could be a function of y. All right? And another way to see it is, yeah, so if this is my f, the partial with respect to x, so if you did the partial with respect to x of this thing that I've got here, yeah, this would be derivative, so bring down that, so that'd be 2, 1 less would be x cubed, y to the 4th, so we're good. This, bring down the power, so yeah, that'd be 1x, and then this, with respect to x, would be 0, right? So you see, it works. But this is important because, yeah, to get it to match with this one, that one's going to be important. All right. Now, so having done that, now to figure out h of y, figure out h of y. What we see here, all right, so if we think about doing here, the partial of this now with respect to y. So this is our potential function, let's call it, f. If I do the partial of that with respect to y, what do I get? So now I've got to start. So I'm on track, hopefully. All right, so if I do the partial of that with respect to y, each term of this, so what would be the partial of that with respect to y? Well, the 4 would come down, so that'd be 2x to the 4th y cubed. That's 0. What's the partial of that with respect to y? Well, whatever it is, it's the derivative. Now, why do I do that? Compare this to my cube. What is that telling me about that? I've got this. So what is this equal to? H prime of y has to equal y, doesn't it? Because that's the missing piece. I've got this piece. Now I need the h prime of y set up to be y. Kind of a roundabout thing, isn't it? Now, I need not h prime of y, I need h of y. So what is h of y here? Well, I've got the derivative and I've backed up to that. I do the antiderivative, don't I? Antiderivative of that's 1/2 y squared. And now that's where it comes in with the constant, the number. That is a positive constant. I've got this figured out because all that was missing here was h of y. I've got h of y now. I know what it is. So, thus, last but not least, f of xy equals, this was my start of it, 1/2 x to the 4th y to the 4th. Plus 1/2 x squared. Plus h of y, but now I know h of y is 1/2 y squared plus c. Ta-da. Okay. Not too bad, but it's, you got to think about it just right. All right, now, One other thing, that part 2 of this. Verify that the gradient of f equals the vector function f, vector field big F. Well, what is, so we're talking about this, the gradient of this thing right here. Again, the gradient of f is a vector where the components are partial of f with respect to x, partial of f with respect to y. What have I got? What's the partial of that with respect to x? Well, bring down the 4, so that'd be 2x cubed y to the 4th. Doing partial with respect to x, that'd be just x. And then with respect to x, that's 0, 0. So then the partial of that with respect to y, same thing, bring down the 4, so it'd be 2x to the 4th y cubed. Doing it with respect to y, so that's 0. With respect to y, that's y, that's y. That's 0. Does that match up? That's the gradient. Is that the same as f? The original thing we started with? Look about the same. The I component matches. The J component matches. And if you want to do an IJK or IJ format, that's fine too. But yes, it works. Okay. Good stuff, huh? All right. Okay. Try this one. Find potential function f for vector field 2x e to the xy plus x squared y e to the xy, that's I, plus x cubed e to the xy plus 2y j. Now, this one, compared to the other one, the first one we did here, I didn't prove that it's conservative. But I did prove this was conservative in a previous problem. Does that vaguely ring a bell? I just did about 10 minutes ago. We did prove this was conservative. So note, we showed this f was conservative previously. Because if it's not conservative, this little method we're doing, no good. Okay, it doesn't do you any good. This only works for the conservative vector fields. Okay, you can't find potential functions if they're not conservative. Anyway, all right. So how do we do it? What was our first step? We've already done it's conservative, so we don't have to do that. Well, what we did was we set, so this part of it, this is our P, this is our Q. All right, and so we set the partial of f with respect to x equal to P, which in this case would be 2x e to the xy plus x squared y e to the xy. And then we set the partial derivative with respect to y equal to q, which was x cubed, which is x cubed e to the xy plus 2y. Okay. So once you got it, because showing it's conservative, it's kind of a little different. They're two separate parts, but we've already done that. So now this is how we find the potential function. Got to keep those kind of straight there. Anyway, all right. Now, what did we do next? Well, what we did next was, on the first one we did this, f of xy equals the integral of p dx. Well, looking at that, that's not looking too fun. Maybe, no. I don't think your substitution is going to work on that. Probably going to be parts. And probably going to be integration by parts twice. If I don't have to, I don't want to. Okay. Over here though, all right. So let's say, not unless I have to. Okay. So over here, so the f of x, I can do the same thing here, except the f of xy, what this comes from, is going to be the integral of q, but with respect to y. You see the difference. So I can do p dx here, the integral, but I think it's going to be easier to do the integral q dy. Isn't it? Look at it. Yeah, that's just going to be the integral of that. X is fixed. The integral of that's just going to be u substitution. And the integral of that's just going to be power rule. That was the way to go. All right. You with me there? You see the difference. All right, so that's the integral x cubed e to the xy plus 2y dy. This one's going to be much easier than that one. Yeah, this one's just a little u substitution, u equals xy, du. I probably should separate it here. So what I'm doing is just doing this plus this. This one you don't have to do. U substitution. U equals xy, du equals x dy. So du over x. Oh yeah, it's even work out. Well, power of x doesn't really matter. E to the u, then du over x. So simplify that. That'll go down to x squared. Yeah, so it's just x squared e to the u du. X squared is just a constant or fixed, so it's x squared. This integral will be x squared e to the u, but u is xy. So chase there. Plus then, this antiderivative is just y squared, isn't it? The only little kicker is that constant. Since I'm dealing only with respect to y here, the constant here could be some function of x, right? H of x. So that's kind of something a little new, that right there, where your constant could be a function of x or a function of y, depending on which one we first. So be sure about that. Careful with that. All right. Because that, yeah. So what we're saying is, yeah, f of xy, a good start to it, a lot of it is this. All right. How do we figure out the h of x? Well, what I've got is over here the partial with respect to x. So let's do the partial with respect to x of this. That would be what? Oh, product rule. So it would be 2x e to the xy plus then x squared times, that would be e to the xy times y. And then that would be doing the partial with respect to x. So that's 0 h prime of x. With me there? See where I get all that? Oh, this good. What have I got over here for each partial with respect to A? I got both of those things. I got this one, it's here. I got this one, right here. So what does that make h prime of x? H prime of x is 0. So what does that make h of x? Because that's really what I need. Well, you got a constant, 0. The antiderivative of constant is, what's a constant? Could be some just number. So h of x here is c. So that's our, it really isn't a function of x, it's just a constant. So sometimes that happens. So final answer, kind of do this, hopefully follow along here. So f of xy would be x squared e to the xy plus y squared plus, we just found out h of x, yeah, that can just be a constant, not really a function of it. Okay? Now, part 2. Is that okay? Any question? Good? Part 2. Evaluate the line integral f dot dr where c is r of t equals t squared plus 1, comma, t cubed, that vector, and t goes from 0 to 1. All right. Here's the payoff for us anyway, for all this. You might be saying, okay, that's great. So what? Well, line integrals. We did those last section. And, you know, they, depending on the function, can be quite fun. And that was a quite fun function. However, if we have a function that is a vector field that is conservative, it's independent of path, the line integral, that was our theorem, our fundamental theorem of line integrals. We can use here, since we've got conservative, which means independent of path, all that good stuff, we can use our fundamental theorem of line integrals, which states the integral over c f dot dr is independent of path in this situation. It doesn't matter what path it goes along. I mean, some line integrals it does matter because, you know, if you go here, 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 that's different than going okay to there. You know what I mean? Integrating it, and that can be fun. But here, we don't really have to do the integration because the fundamental theorem says you just do f at r of b minus f at r of a. This f that we're talking about is this, you know, this is part 2 of this particular problem. What's my f? That's my potential function right here. Here's my f, right there. So if all I have to do is figure out r of b and r of a. In this case, it'd be f of the r, the b. This is b, this is a. Just the r function evaluated at the endpoints. So it'd be r of 2. No, what do you 2? R1 minus f of R of 0. With me? I don't have to do this integral. I just have to do, I've already kind of done it, I guess, in a way. But the antiderivative part of it. Yeah, what's R of 1? R of 1, just plug in 1. 1, 1. Right? What is R0? 1, 0. All right, so last but not least, f of R1. So f of R1, the x is 1, the y is 1. So it would be 1 e to the 1, first part, plus y is 1, plus c, of course that's going to cancel out, minus the r is 0, well, r is 0, you got x is 1, y is 0, so that would be 1 e to the 0, y is 0, c's will cancel. So we've got e plus 1 minus 1. Oh, how about that? Right up with e. Okay, let me, any questions about that? Let me show you one more. We haven't talked about proving a vector field with 3 components, I, J, K, a three-dimensional vector field, if you will. Proving that conservative. But here's what we can do. If we know the vector field, three-dimensional vector field is conservative, we can do the same sort of thing. I think I've got a couple of those picked out for you, so here's maybe how we can do that. Find a potential function f for conservative, so provided I'm giving that it is conservative, vector field f equals 2xy cubed z to the 4th I plus 3x squared y squared z to the 4th j plus 4x squared y cubed z cubed k. So you're not going to have to prove these are conservative, the 3 component vector fields. I'll save that for another day, another year, something. All right, but here's what we can do. We can still find it the potential. If we know it's conservative, we can still find the potential because it's really just extending what we've done before. So it's kind of another example of doing this. All right, so what do we got? We got P, we got Q, and we got an R. Guess what? If it's conservative, same thing holds here. The partial of P with respect to X, the partial F with respect to X, guess what it equals? Partial of f with respect to y, again, we're trying to find this potential function f. Here's what we know, with this being conservative. We know the partial of f with respect to x is p. So it's, I guess I should have written, it's 2x y cubed z to the 4th. We know that the partial f with respect to y equals q, so that equals 3x squared y squared z to the fourth. That's what the partial of f with respect to y would equal. And then, guess what this equals? Partial of f with respect to z. 4x cubed, 4x squared, y cubed, z cubed. So it's just adds one more piece. So how do we find f? Well, we got to do maybe a couple of integrals here, antiderivatives. So f x y z here. If I get f from this one, what would it be? Well, since this is a partial with respect to x, it'd be the integral of p dx. Right? Does that look? How does that look as far as doable? Yeah. Any of these is probably doable in this case because it's just one part to each one. So I don't think it'll matter which one we do first. So how about this one? Let's just go with this one. That's going to be easy. Because all I'm doing is integral with respect to x. The y and the z are fixed. So that would give me add 1, so divide by 2, right? The x squared, y cubed, z to the fourth, plus a constant. But what does the constant here entail? What could the constant entail here? Well, since I'm doing antiderivative with respect to x, the constant could entail a function of the other two, y and z. So yeah, unfortunately, the other part could be kind of complicated. It won't be too bad. So here's how I use the other two, all right?